All right, looks like it's streaming to Twitch now. Let me make sure the audio sounds right. Yep. Okay, so all right, now that we're finally started, what do we want to look at? Does anyone have any questions so far on the baby Rop module? Level 4. All right. Let me start taking a look. And there's also another question for level 7. All right, let me start by launching level 4. Okay, so let's see here. If we run, let's just start by running level 4. And for the person asking about level 4, do you have any specific questions that you're interested in for level 4? Yeah, so the question on Zoom is related to basically dealing with the flag string. So you specifically said, like, can you repeat again, I guess, what do you just want to generally see what it looks like for us to put a string on the stack for our Rop gadget? Okay. Yep. Okay, so I'm trying to see exactly what level 4 tells us. It says ASLR is on as per usual, and it leaks us the address of the stack. So I believe that this is just like the prior 3 levels. I think that the difference here with level 4 is that we do not have a win function or any variant of a win function. We kind of have to truly build everything up with very small little Legos, as Jan likes to use for a metaphor. Okay, so in order to first approach this string problem of getting the stack or getting like /flag onto the stack for our string, we first need to see what kind of gadgets we're working with so that we can see that address get used, I guess is the way to say that. Okay, so let's see here. I think this is the right syntax. And we'll just type that into less. Okay, so let's see what kind of gadgets we're working with. We're looking for, so for instance, like if this binary that we're going to be able to use ROP gadgets from has a syscall gadget, that would be especially useful. In fact, we can see if it has a syscall gadget, and it looks like it does here at 4024EF. So that will definitely be useful for us. If we have a syscall gadget, that means that assuming we have the other necessary gadgets for setting up our registers, we can basically just do arbitrary code execution, similar to traditional shell coding. So that means we don't need a win function or anything crazy, or we don't need to try and like start leveraging functionality that necessarily specifically exists in the binary. We can just take complete advantage of this syscall instruction. Okay, and then so let's see what else we have. Do we have a pop RAX? We do. Do we have a pop RDI? We do. Do we have a pop RSI? We do, and I don't know if we'll need it depending on our payload. We probably might. I think we'll need that if we want to do like send file. Pop R10 exists. Okay, so we have absolutely everything necessary for doing an open send file. And then now we need to just figure out how to structure it and how to get our /flag data. Yeah, was there a question? Yeah, you could call any syscall you want. You could call chmod as well to just change the permissions of the flag. Either one will work. I guess chmod might be a little bit easier because you just have to execute one syscall in that case rather than open and then send file. Let's start by, how do we want to do this? Let's start by just calling open on it, just to see what it looks like to create our Rop payload. And yeah, exec.ve master race, yeah, that one's also useful. You could have an arbitrary binary and just let that run. Okay, so let's see. Let's call just open as a random one. So in order to do open, we will need to, let's see here, quickly pull up this syscall table because apparently memorizing syscalls is impossible. Okay, so sysopen is going to be 2. So what we need to do in order to call open is set RAX to 2. In fact, let me start a multi-line comment. Here's what our general strategy is going to be. Similar to shellcoding, basically no difference. It's just going to be a difference in the structure of what our payload actually looks like. So we need open to be to 2. We need RDI to be pointing to a string containing, say, flag. Pointer to flag. And then we want RSI to be equal to 0. And then we want to do syscall. Okay. So we just quickly wrote that out as our general game plan here. So in order to get a pointer to flag, we're going to need to be able to write data somewhere. So obviously we're putting all of our payload on the stack, so the stack is a great place to put /flag. But of course this requires us to know where the stack is. And fortunately for us, this level, as well as many other levels, actually leak out to us exactly where our input buffer on the stack is. So using this, we can basically know where our flag pointer is, or how to create a pointer to flag, because we can just put flag on the stack and then we know where that is, so we can easily create a pointer. Okay, so let's start by importing pwn. Let's do process equals pwn dot, why is this like the most recent thing? Whatever, let's just write ourselves. Process equals pwn dot process baby rop. Okay. So let's start by doing process.read, and we're not going to completely just script this out. We're just going to, how do I want to say this? We're going to just do this interactively. Let's see here. Okay, so let's call process.read 4096, and let's just print that decoded with Latin in case anything weird's there. Okay, so now we know what our input buffer is. So input buffer is here. And of course we could do a receive until and such. And then, let's see here. Actually, we still need to know our distance from our input buffer to, are we not on teaching? No, we are on teaching. Oh, is there more data? I feel like there's teaching data that tells us how far we have to write. Is there not? Huh. Don't know what that's all about. Okay, whatever. So let's actually then, in that case, start by figuring out an easy way to figure out how far we have to write is to just get the program to crash. I don't think the teaching had that this time. Huh. Could have sworn it did. Whatever. I guess that's a separate issue. Let's do it ourselves, though. So we can, how do we want to do this? So an easy way that I'm thinking of for doing this is just repeatedly send increasing number of A's until we get a crash. Seems like a potentially straightforward way to do this. So let's go with while true. Or we can use a cyclic pattern actually. Then we'll have to do no suid. Okay, let's do this correctly. So let's make our current working directory be temp, and let's do the following: import pwn.process equals that, and then pwn.cyclic, is that it, right? Yeah, pwn.cyclic. Or actually, hold on, we created the process incorrectly. We can actually pass it a set UID equals false. I think we'll be able to core dump with that. We'll see though, just to verify. And then process.write pwn.cyclic, and let's go with 256. And then let's do process.readAll, and just in case we want to look at that, data equals, and we can see we got our seg fault. So the next question then is, do we have a core dump? And we could see if we have a core dump. Looks like we do, and that was, I think, just created, hopefully. I guess we can very quickly see if it's not. And then let's go with pwn.coredump on this core file. Okay, and then we have our coredump.stack. And in fact, we could quickly look to see if what we read back. So when we received this, there was a stack address here. We can quickly make sure that that stack address falls in here to make sure that this is the correct core dump. And actually, this is even easier. We can probably just use this straight away to determine our distance. We don't even have to analyze the core dump, but you know what, let's just analyze it anyways, just in case you're not on teaching, you're on testing and you want a refresher on how to analyze a core dump. Okay, so core dump.stack and I think we can go core dump.rsp to core dump.rsp plus 8. Yep. Okay, and then we can do pwn.cyclic find. And it tells us 136. So if we send 136 A's, we will be right up against there. So let's quickly just confirm this. Let's take 136 A's. We can even run it outside of pwn tools just to be absolutely sure. If we send this, oh, interesting. Huh. Oh. Oh, right. If we send 136 A's, the next data that we send will be overflowing the saved RIP. And you can actually see in the case where I ran it outside of pwn tools, where I did 136 A's and then also a new line character at the end. This new line character shows up in our address. So we send 136 A's, and then whatever we want after that will be executed. So let's start by doing a, let's say, pop RAX. So there's actually some cool things you can do in pwn tools for scripting ROP. So what we can do if we construct, let's just recreate our process again. So we have this process, and then we can do elf, and we can do pwn dot pwn.rop on that. So there we go. And you can already see actually in this output message that it loaded some gadgets. So what we are interested in, and in fact, let's just start by doing a exit ROP payload just for complete sanity's sake. Let's do rop.findGadget. So this is the syntax within pwn.tools for finding gadgets. I think in general, though, it's better to use RP++ for doing an exploratory process of trying to see what kind of gadgets you're working with. But once you know what gadgets you're working with, you can just use pwn.tools for doing a find gadget to find that specific one. So you know the exact address in this scripted way. So what we're looking for is pop RAX and then ret. So this is the syntax for that. And we can list them all out. Or can we? Yeah, there's a question. What's the question? Mm-hmm. Yeah, of course. I mean, you can do whatever you want for your workflow. So the question was just use RP++, copy the address into your pwn.tools script. Go ahead and do that. I personally prefer my scripts to be a little more readable. So rather than just some random address showing up, I like to know that pwn.tools agrees and found that gadget. That's just kind of a preference thing, though, for making, I guess, your code a little more readable. But I mean, really, it doesn't matter if you get the solution, you get the flag, you get the flag. Okay, so and if we used RP++, so that why? I don't really know what just happened there. Oh, this terminal's slightly messed up. That's kind of annoying. Okay, anyways, though, let's continue on. So we have our pop RAX gadget. So we can say that. And then we can find our syscall gadget. So we can do exactly the same thing. Find gadget, syscall ret. So now we have pop RAX, and it tells us the address of it. So you can do pop RAX.address. And of course, if you did hex to like see that this is the same in a more readable way, it'll tell you the address, it'll tell you the instructions involved, and it'll tell you the modified registers. And maybe this is probably saying that this gadget is an 8-byte address, so that if you're on a different architecture, for instance, it knows how to deal with that. Okay. So we have our pop RAX, we have our syscall gadget as well. We learned that we need 136 A's, so did we find that here? Yep, we still have that. So now if we do process, where is that, equals this. Okay. And then what we can do is call, so let's instead of calling open, let's start by calling exit just for a sanity check that we're successfully ropping. So sysexit is syscall number 60. So if we create our process, and then what we do is process.write 130 or A times 136. Plus pop RAX plus pwn.p64, say 42. Or excuse me, the 60 needs to be our, oh, and in fact that means we're missing something in order to do sysexit. We still need our RDI gadget, our pop RDI. So let's quickly find that. So with the same way we did pop RAX equals this, we can do pop RDI. Oops, that messed that up. Let's quickly fix pop RAX, and then we can say pop RDI equals this. And then we can go back to writing our payload. So we're about to send 136 A's. And then the next thing is going to be the address of the instruction that gets executed next. And that is going to be pop RAX. We're going to put the syscall number for exit there, which will effectively put 60 into RAX. And by popping this off the stack, because you have to think that from here on is your entire Rop payload, the first thing that gets executed is this. This pops this off the stack, which means 60 is in RAX, and the very next thing on the stack is going to be what gets executed, because this is pop RAX and then ret. And you can kind of think about conceptually, everything in your Rop payload is just a bunch of pops, including the ret. The ret is really just a pop RIP. So it's just a bunch of pops all the way through. So the next thing we want to call is pop RDI in order to set the value of what we're going to exit to. Just verifying, yep, we got our pop RDI there. And whatever we put here now is what RDI is going to be set to. So in this case, let's just go with 42. And then we want to do our syscall. So similar to how this pop goes, these two kind of go together. It's basically setting RAX to 60. These two go together. And then the next thing is going to be our the next thing will be also executed, which in this case will be a syscall instruction. So if we send this, in this case we have messed up. What we can do to correct this, so there's kind of a number of ways to convert these pwn tools gadget things. You can see here, right? This isn't just like a well-formed gadget. I think there's a number of ways to do it. A simple way using what we've already seen in the past is just pwn.p64 and take the address of pop RAX. And we do the same thing here. Pwn p64, the address of this instruction, or of this gadget. And again, pwn p64 address. Okay. And then we can do process.readall. Get some stuff going on. And then we can see, do we see what we exited with? Yes, we do. Stopped with exit code 42. So we have successfully executed our Rop payload to cause the program now to do an exit code 42. Okay, so now we can just generalize from this. We've already shown that we can basically do whatever we want. The one thing here that's missing is what if we have string data? So we can deal with that, and that's kind of what we set out initially to look at. So let's do that now. So let's create a new process. And then let's go ahead and process.read 4096. Because what we need to know is where our input buffer is located at, or more specifically, we need to know where the stack is. And once we know where the stack is, we know where everything on the stack is. But conveniently, it tells us specifically where our input buffer is, which means that very first A that we send. Man, this is sad. I can't scroll up. It does that annoying thing. As we saw before, when we sent 136 A's, that very first A is going to be located right here. So what we can do is let's go ahead and say that this is our stack address. Stack adder equals this. Actually, we'll even call it input adder equals that. Yep. Okay. And then, okay, how do we want to show this? Yeah, maybe using CH module will actually be the quickest way to see everything we've been talking about. So I'm going to hit Control-Z to background this, and I think that might make things a little more confusing, but yeah, it does this annoying thing for some reason. But anyways, if we look at the permissions of, oh, I could have done this in IPython. Let's actually forward again, and we'll show, we had that anyways. And then if we do ls/al/flag, we can see, of course, as per usual, the flag is read only. And then let's go ahead. In fact, this input adder is not going to be correct. The reason I need to actually create the process again is because we were doing set UID equals false, and that will make it so it's not executing with root permissions. So let's go ahead and do that again. And then let's do process.read4096 to get our input adder again. Print that .decode. So we can see input adder will be there. So we'll just manually do it rather than, of course, the probably more sane way to do this is to create a script that will read until this is located at and then parse this out or whatever. But we don't need to do that. I messed up copying it. Okay. So now let's look at what we were writing before. We were doing this in order to exit to 42. In this case, let's go ahead and do our chmod syscall. And let's modify this to make that happen. So chmod needs 90 in RAX because that is the syscall number for chmod. And then in RDI, what we're going to do is instead of put this 42, we're going to put, as you'll see, we're going to put input adder here. And that would currently imply that we're about to chmod like a bunch of A's with whatever permissions we do here. I'll explain it more as we go along here. So syscall is here, but that's not enough. We still need to set our, yep, there's a question. Mm-hmm. Mm-hmm. Yeah, so the question in Zoom is that basically the chmod was executing correct, or it was executing, but the file permissions of flag were not being set correctly. So my theory on that would be that you maybe weren't using octal for specifying that address. Let's see if we run into the same issue, and maybe if not, we'll, yeah, go ahead. Yeah, but did you do octal 777 or just 777? Yeah, so that's the issue. The permissions need to be an octal number. It's not decimal 777, it's octal 777. So we'll see what that looks like here. Let me put flag here at the start. So flag dot, and then I think it's ljust and 136. And in this case, let's just, yeah, we can keep doing A's, why not? But we need to get a null byte as well at the end of this flag. Because the path, of course, is a string, and C strings are null terminated, so of course got to make sure we're null terminated here. Okay, so we've got pop RAX, 90, pop RDI, input adder. So this input adder should be pointing right here because input adder is the beginning of the stack, pointing right there. That's the beginning, or the beginning of our input buffer, which this is the beginning of our input buffer. And we're actually missing something though. We need, so similar to how we created pop RDI, we actually need a pop RSI as well, which I don't think we have currently found. There we go. So we've set up RDI. The next thing to do is set up RSI. pwn.p64 pop RSI.address. And then what goes here is going to be the permissions we want to change /flag to be. And what we want to change them to be is 00777. So not 777 decimal. In Python, the notation for writing out an octal number is 00. 777. Because, yeah, I guess the thing to realize here is that file permissions follow kind of a octal number scheme. Basically, it needs 3 bits per field in the permission model to indicate read, write, and execute. And a 3-bit number, of course, follows naturally with octal. So that's kind of why that is the case. Okay, so this should chmod our flag. Let's see. Nope. Hold on. Maybe we need to read all. What? Oh, did we recreate the process and then not set up our address? Hold on. Let's see here. If we do, so let's run through it again. If we do process equals that, let's do process.read 4096. And then input adder equals this. And then let's go ahead and write. Let me quickly look through this. So this is flag, this is pointing here. We're setting 90 to RAX. We're setting, well, then we're doing a pop RDI, and we're putting this input adder in there, which should point here. And then RSI, and then permissions, and then syscall. Okay, let's see. Maybe we messed up before. Let's see if this works this time. And then let's do process.read. Oh, I see the issue. We're missing a slash at the beginning, and we're currently located in the temp directory. Yeah, currently in the temp directory, we're missing a /. Let's go ahead and fix that. Let's run it again. Process equals that. Read 4096. Input adder equals this, which comes from here. And then let's get ready to write. And this time let's put our / in the front so that we're actually chmodding the correct file. And then we can do a read all. Why is this not read alling? It seems to have worked. I don't know. Could the pipe have been interrupted? Let's run through it again and see what's going on. So we do a, what am I thinking right now? We want to recreate the process, read 4096, input adder equals this, and then we write that. And then if we did process.read, say 1 byte. Okay, so stuff is happening. I think we can do read repeat 0.1 will give us everything it can read. Let's see if that works. Okay. Received 192 bytes. Is the next address on the stack? We can see, I guess. I think we print 1 extra. So after our syscall, we have a ret 401190. Is this returning back into main and looping? Does it actually happen to be on the stack? Let's see here. So we're thinking about 401190. Actually, we can do it from here. Objdump -d and intel. So we're looking for 401190. 401190. It's pretty funny. So we actually couldn't just sit there and wait for the process to execute. As it turns out, the very next gadget that we didn't actually put there, but was already on the stack for us, was a pointer to start, which means that the program actually just looped itself, which is interesting, right? You can think of it as we went through, we did our exit or our payload, And this is maybe a segue, I guess, into some of the later levels that there comes in some cases you actually don't have leaks for everything that you're interested in, but you can run a ROP chain to leak out an address, and then you can just restart the program. And now you have the address of what you're interested in, and you get to run a new ROP payload knowing that address. So kind of interestingly, just based off of coincidence of how the stack was set up here, our program actually just looped itself unintentionally. That's pretty funny. But either way, that showed that, and this was kind of what it looked like. Yeah, there was a question? Yeah, if there was... so there's... If we wanted to use this to leak the stack canary, the issue here is that we have an input buffer, and we're just overflowing that input buffer all the way into... we have an input buffer, and we're overflowing all the way into the saved return address. And you couldn't actually execute your ROP payload if there was a canary blocking you, right? Because before it was able to do that ret that starts executing your ROP chain, you would have overflown the canary. But you could use it, for instance, if... So let's say we didn't know where let's say that this leak didn't come to us. It didn't tell us your input buffer is located at blah, blah, blah. But we really want to get /flag on the stack and be able to have a pointer to it that's relative to the stack. What we could do is we could construct a ROP payload that, knowing that there's going to be a stack address probably somewhere on the stack, use that to, like, say, puts out that address and then restart the program. And if you puts out the stack address and restart the program, now you've basically given yourself this leak, even if the program didn't give it to you. So we're kind of being... Is there a question? Yeah, so are you familiar with the C function puts? So yeah, the argument to puts, what you would want to do... actually, that's a good question. Maybe that doesn't exactly work for a stack address. There's probably a way to get that to work with a stack address, but I'm saying, like... So something you definitely can do with puts is leak out an address of libc. Because what you can do is you can... so if you... How do I explain this? Let me quickly pull up Paint. Maybe that's the future. Let's see if... Yeah, so the way... Second level 3. We'll look at that in a second here. Yeah, I think this one's cool. Okay, so the way, I think Jan at least briefly, what does this say? Move this window away from the shared. I have no idea what this is all about. Can you see Paint, right? I think it shows up. Okay, sweet. Okay, so your program calls puts, right? Call puts when it wants to write out data. This is how we print the, like, this stuff, or I guess that's a printf, but I mean, you call puts, right? So the way that works is it's actually calling puts at PLT. Okay, and the way puts at PLT works, in fact, we can probably more easily actually just look at this. Foreground, opt dump. So we can see that there's this puts at PLT, and you'll see that when your program's calling puts, that's what it's calling, is puts at PLT. So puts at PLT, what it's going to do is it's going to jump to this dereferenced address. So it's going to take whatever is located here, dereference it, and jump to that. And what's here is, why does this say at glibc? There should be a puts at got. What? Oh, right. I think objdump doesn't know how to look at this. Okay, so let's go back to paint and just kind of roll with it. So we have a PLT and we have a GOT. So this just says to jump. This is kind of insane, but we'll quickly just roll with it. To dereference puts at GOT. And this, so this is when we jump here, so our program calls puts at PLT, it goes here. This in turn dereferences whatever puts at GOT is. So let's say right here is puts at GOT. The address that's located here, the very first time we run through this, is actually something that just goes back into the PLT, but further above. So maybe we can see that in objdump in this case. Puts at PLT. Oh, it's the sec thing. Is there, can we see resolve? Basically, what this is pointing at is a resolve function, which will load the address of puts in libc and put it here. So that now this is pointing to libc. And then it will call into that. So basically, what I'm really ultimately trying to get at here is that we have this puts at PLT, which allows us to call puts. This is how we call puts on something. This is PLT. And what we might want to call it on is puts at GOT. Puts at GOT. And if we call puts at PLT, if we pass that puts at GOT, what's going to be here is an address in libc. This paint idea is maybe too insane right now. Need like a tablet or something to actually write this out. Anyways, what will be here at this address is a libc address. So what you'll do is you'll end up writing out the address of a libc address to standard out, which means now you know where libc is located and you know everything in relationship to libc. Does that at all make sense, or is this kind of like way too crazy from this explanation? Okay. You don't have to, so there are useful things for overwriting this value. So for instance, if you were to overwrite this value, you could make it so that when you call puts, you don't actually call puts, you'd call something else. But it's very common these days for binaries to have full rel row, which basically means that this GOT gets initialized at the very beginning and these addresses become non-writable. If it doesn't have full rel row though, these addresses are writable and you could in theory change things, but that's definitely not going to come up in this module. But that is definitely from a security perspective, you could think like, hey, what happens if I overwrite this address? And it's like, yeah, now if anyone calls puts, they're not actually calling puts, they're calling something else. And that is, in some cases, a very useful primitive. But it's largely mitigated through full rel row. In general, though, you're trying to leak out a libc address, and you know where a libc address is in the binary, it's at puts at GOT. So if you do what's called like a puts, right, where the outer puts is puts at PLT because that's how you actually call stuff, and the inner puts is puts at GOT because that contains the address to a libc function. what you end up doing is leaking a libc function. And maybe if you have more questions on that, I can link you to an article that just explains this in much better detail than this awful paint attempt. You're saying with 5 and 6 there's no leak. Let's see. Take a quick look. And someone also was curious about 3, which if the person that has a question about 3 could expand on maybe what their question is with 3 that like 4 doesn't answer, that'd be very useful. Okay. Eventually it'll SSH. Maybe. Or not. Okay, let's try that again. Okay. Yeah, so it definitely doesn't print out any hints. That's definitely true. Trying to remember. So if we run rp++ on baby Rop, so something that, actually first let's run checksec on baby Rop so that we know what we're working with. And we can see that there's no PIE, which is very useful in this Rop context, because when there's no PIE, that means you immediately know where a bunch of gadgets are in the binary. So next, let's run rp++ and see what kind of gadgets we're working with that are in the binary. fr2. So maybe one of the first things that I am very interested in as a gadget is to see if syscall exists. And it looks like it does in this case. And now if we have pop rax, which we do, if we have pop RDI, which we do, pop RSI, we do, pop R10. Okay, so basically we should be good to go in terms of doing arbitrary syscalls. But as you noted, there's a little bit of an issue here in that we don't know where the stack is. So it didn't like alert us that anything, actually we can see, yeah, we can definitely see that there's not like some ASLR disabling mechanism, because this is at like a random looking address. If we ran it again, we would see that this address changes. Yeah, this just changed. And this technically is a stack address, but we don't get to know this when we're sending, and this is also just on teaching. So basically more of the story is, as you said, we don't know where the stack is. So you have a couple options. You can do what we previously discussed, which is, well, I guess we discussed leaking out a libc address. I'm trying to think what to say without just straight up giving it completely away. So something to think about is that there's a bunch of strings in this binary that already exist. And as it turns out, so for instance, say like this welcome to, or like this exiting message, or all of these strings actually exist at known addresses. You know, in the same way that you know where all these gadgets are, like these kind of useful instruction primitives, you know where some data is as well. in the case of like a string. And even if we didn't run strings, right, there's going to be all sorts of, in the same way that you don't have to just ROP to like a complete function, and how you can ROP into like these potentially even like inter instruction boundary things. Like, you can find data anywhere, and you know where a bunch of data is in a bunch of strings. And you can use this or any string in conjunction with the fact that you have control over this system in terms of creating files and such, to kind of leverage these two things together, right? You might really want to have, so for instance, if we could like search through all of these strings that exist and find like /flag, which clearly we don't, like you would be happy. You wouldn't need to put flag on the stack. In this case, you would know where flag is in memory. And you can actually, so for instance, if you want to see in pwn tools, let's say for instance this exit, where is it? So that we know that exiting exists in the binary. Let me demonstrate that a little bit with pwn tools in terms of like, so where is exiting in the binary? If we open IPython, import pwn elf this, and then if we do like elf dot search, we can actually look for this exiting string. And if we just bring that out to, I guess, so this returns a generator that's going to basically just start yielding off whenever it finds exiting. And in fact, let's make sure there's a null byte, because we're probably interested in a null terminated string. And let's just call next on that, which in the case of a generator will give us the next one that's available. And let's call hex on that. So as I said, say instead of exiting being there, /flag was there. You wouldn't need to write /flag to the stack anymore, because you would know where /flag is. It would be at this address. Unfortunately, /flag, and we can actually quickly look for it, and we'll even not include the slash, because in theory we can make our current working directory be wherever. We can see that it's not finding it. And as I said, similar to how you can make your current working directory be wherever to start having influence on the system outside of what you send to the program, right? Like I can do /touch temp a if I put that in front. Now temp a exists. This is a file now that on the system relevant to this program. So now, let's say I search for A. Don't have it, that's fine. Let's search for B. Apparently there's a B followed by a null byte right here. If I touch temp B and I cd into temp, now we have, wait. Oh yeah, this has our B, okay. Now we have a string that in some sense is pointing to this file that we just created, right? This B null byte could be interpreted as this. This already exists in the program. So what if this B was something else, right? You could think of, rather than just making it this empty file, it could be, without completely going too far into just giving away this thing. And you've kind of explored this potentially in previous challenges of leveraging the system in various ways. This B could be very useful to your exploit, even though the program itself isn't aware that this exists. When the kernel starts acting on file paths and stuff, if it exists, and it'll use it. So I don't know, so think about that for 5 and 6. Exactly. Okay, so there was a question on 3. If you have time, can you go over level 3 quick if you don't mind? It can be after, well, let's go to 3. I want to make sure we do earlier levels before we do later levels. So jumping from function to function mainly is what I am having issues with. I want to ensure I'm doing it right. Oh, right. You did message me earlier about this. Okay, so let's go ahead and start up level 3. Okay, so now let's start by running it. We can see that in this challenge there are 5 stages of win functions. So thinking back to level 1 where there was a 1-staged win function, and then level 2 where there was a 2-staged win function, this has a 5-staged win function labeled win stage 1 through win stage 5. Guess the walkthrough is not nice enough to tell us exactly the addresses of that, but I'm sure that's fine. We can find them on our own. In addition to going to each function in the correct order, 1 through 5, you must also pass an argument to each function you visit. The argument you pass will be stage number. For instance, win stage 1. Okay, so we want to pass 1 to 1, 2 to 2, 3 to 3, etc. Okay, and then just to make sure, let's also run check sec on this binary. Oops. Man, I don't understand why this doesn't tab complete. Okay, so as we are hoping for in this context of ROP, that pi is disabled, which means we know where a bunch of gadgets and functions and whatever else are going to be. Of course, if pi was turned on, ROP is still possible. It's just now you're going to need to get a little more clever, as you'll discover in later levels. More clever being, if you think back to like when baby Mem, pi was suddenly turned off. You could do like a 4-bit brute force and that sort of thing, right? Because there's going to be some return address there. It's just not necessarily the right one, but you'll get there when you get to those levels. Anyways, let's keep looking at level 3. If we do objdump -d -m intel baby ROP level 3 less, we were told that there should be like a win 1. Let's just look for win. So we can see there's win stage 3. There's this flag size thing. This calls this flag size thing. You could probably guess that maybe it's going to print out parts of the flag. Maybe that's what the stages are doing. Win stage 2, win stage 1, blah, blah, blah. Win stage 5, win stage 4. Okay, so all of our stages are in there. So what we want to do is we want to execute those functions. So the way to do that, let's see here. If we open up IPython and we import pwn and we say that process equals this, but instead level 3. And then the first thing we need to do, of course, is know how many bytes we have to write until we start overflowing the saved return address. So let's do our trick that we did in level 4, where we use a cyclic pattern to write 256 bytes of this cyclic pattern to the program. And then let's do a process poll true to just make the program be done. Actually, we need to do, we need to make this not SUID so that we can actually analyze that core dump. Let's go ahead and switch into temp so that the core dump will be placed into a writable directory, and we can run it with set or with the disable SUID parameter. So let's go with IPython, import pwn, process equals this, and set UID equals false. So that will invoke the process with suid disabled, which will allow us to have a core dump pop out. And then we can do process.write that, and we want the process to run until it is, oh, paint is still open, yeah, sorry. Let me close that, at least for the time being, until we want to venture back into paint. Hopefully not, but maybe it'll be useful. So process.poll true to wait for the process to die. And now we should have a core dump, and we do. So what we want to do is the same thing we did on level 4 to analyze that is, what was it, like cyclic find, yeah, this. Or I guess we need to create our core dump first. Core dump equals, by the way, in case anyone's curious about how I'm like quickly switching between things, which I guess you might be. So inside of IPython, you can hit Control-R. And when you hit Control-R, you see that this iSearch backward thing pops up. And it'll basically search through your history of things that you've done in the past. So that's how I'm able to like quickly re-execute things. So if I hit Control-R and I just start typing for something that was in my history, so say like core, right? We can see that this ls-al core pops up. If I add the deferred core dump, we'll see that this pops up. And what we're really interested though in is like core dump space, because that's going to be how this gets assigned. Okay, so this will construct our core dump. And then we can do our other core dump thing right here. pwn.cyclicFind, where we take our core dump stack and we look at right on the stack where we were about to ret to. Cyclic find that, and it'll tell us how far away until the saved return address is being overflown. And in this case, that is 72 bytes. Okay, so now let's think here. Okay, so what we need to do in this case for level 3, which has a bunch of functionality for allowing us to call into these win stages, and so we don't want to just necessarily use completely arbitrary gadgets. We want to, I don't know, we'll at least follow what, maybe there's other solutions than having to use these win stages, but let's go ahead and humor it and go through what it's designed to do. It'll probably be actually the easiest way to do it. So what we need to do is that, let's start by just creating this multi-line string. We want to call win stage 1 with 1, and then we want to call win stage 2 with 2, win stage 3 with 3, and so on. Okay, so in order to do that, this is going to translate into, so we need to put a 1 into the first argument of win stage. And 1 second here. Okay, anyways, let's continue doing this. So we need to put 1 into the first argument. So we want to set RDI to be 1. And then we want to call win stage 1. Similarly, RDI 2 and win stage 2. And then finally, RDI 3, win stage 3, and so on and so on. So in order to do this, to further expand our thinking here, what we want is a pop RDI ret gadget. If you think of, if everywhere I put parentheses is basically going to be an 8-byte value that goes on the stack, we need a gadget that's going to set up our RDI for us. And then we want an 8-byte little endian representation of the value 1. And then we want the address of win stage 1. And of course this continues on. Win stage 2. And just to keep consistent, we'll show 3 of them. Win stage 3. And so on. Okay. So the correct way to do this would be to explore and look through RP++ and see if there's a pop RDI ret gadget. Here we're just going to hope there is. So pop RDI, so we will use it similar to what we did in level 4 to get this RDI gadget. We will rop dot, or I guess we need to set up what rop is. Rop equals, do we have elf? We don't. Okay, let's grab a pwn.tools elf for level 3. And then let's do rop.rop, or oops. Instead of process.elf, let's just pass it this elf we created. And then let's do find gadget. In fact, let's do RDI, pop RDI, this. Okay, so let's just assume the binary has it, and if it doesn't, then pwn.tools will complain that it didn't find it. Turns out the binary has a pop RDI gadget for us. Okay, so now what we need, let me remember how many A's we have to write. So now what we need to do is that we need to call process equals this. And in this case, we will remove this set UID because we don't care about the core dump anymore. And then we will process.write. Let's just start writing it out. We want 72 A's, so 72 A's to get us so that we're right up next to the saved return address. And then what we want to do, following from this plan that we created, because we want to call win stage 1 on parameter 1. In order to do that, we need RDI to be set to 1, and then we need to call win stage 1. In order to do that, we need this sequence of gadgets. We need pop RDI ret, and then 1, which will put 1 into RDI, and then it will ret. And ret will basically do a pop RIP, and the current stack pointer will be pointing right here, which means we will resume execution here. So that's kind of how to think about it, how you have these sort of code and data interleaved in these ROP gadgets. So that really you're just doing a bunch of pops, and as long as you track your pops for data and track your pops for control flow, everything will be great. Yeah, okay, so we need, as we said, a pop RDI.address and pwn.p64 of it. And remember that all of these things are 8-byte values, because as we said, we're doing a bunch of pops off the stack, and the stack, when you do a pop, is going to pop 8 bytes, so you can't make this like 1 byte or like 4 bytes or something. It needs to be 8 bytes. Everything works in 8-byte increments, including whether it's addresses to instructions or the value that's going to get popped in. Okay, so then let's go with pwn.p64 1, and then let's call, we will, hold on, let's quickly show something. So if we look at our elf that we have here, we can see, we can look at all of the symbols. This is a nice thing that pwn.tools lets us do. We can look for this win stage 1 inside of the symbol table, and it actually tells us now where that's located. So we can see that win stage 1 is located at this address. So when we go to do this gadget here of putting this in here, that's what we're looking for. And of course, we need to continue to do pwn.p64 to make that happen. So let's go back to writing this. So pwn.p64 elf symbols win stage 1. And let's just start with that. Let's write that. And then let's do process.readAll decode print. So we can see that some portion of the flag just came out. And as it turns out, you can just keep layering this strategy to call the further ones. So let's see here. If we were to recreate a process and then process.write, and in fact, let's quickly make this easy for ourselves. Let's go ahead and do def win stage, and we'll just have this spit out to us the gadgets necessary to do this. So we can do pwn.p64 pop rdi.address. Actually, let's just copy this. And that, and let's clean this up so that it's parameterized. We want stage to go here. We want to use an F string. Make stage go here as well. Okay. So now if we do win1, we get that gadget. If we do win2, we get this. You can see that this 1 turned into a 2. And we should see near the end here, we've got some more stuff changing. That's calling into the different win stages. Of course, at the beginning, our pop RDI is consistent. Okay, so now let's do process.write. We just need 72 A's. And then we want to do plus win1, plus win2, plus win3. And you'd want to do all 5, but let's just do this so we don't leak the entire flag, since this level gives us the opportunity to not leak the whole flag. You can see that as we go, we just start leaking up the flag bit by bit. So something to think about here, maybe a potential trouble spot you might find yourself falling into in doing this, is that you might be thinking back to, like, say, baby mem, where there would be a parameter check that would, I believe in baby mem there was some level that basically checked to see if the parameter was like hex 1337, and if it was, only then it would print the flag to you, and the solution is to just jump past that. In general, that doesn't exactly work for ropping, and here's why. Let's take a look at win stage 1. Okay, so what I'm showing is jumping straight to the beginning of it, and you'll see that when you jump straight to the beginning of it, it has effects on the stack. It pushes RBP, pushes RBX, it does all of these stack manipulations. And if you jump partway into it to skip over the check, say you want to just like maybe just jump here or something, you can run into issues. Because if you just jumped straight here, it'll work through the first stage. But if you need to call more stages, you're going to have an issue, because this is going to have all sorts of effects on the stack. So for instance, it will add 28 to RSP, which is an issue, but potentially, let me think here. Yeah, you could overcome this by just putting your gadgets further along. This is fine. You could think of this as like several pops that are not important. But it'll also, and you could even not care about this, you'll just pop RBX. And then, yeah, this is the issue though. Is this pop, is that an issue? Pop RBP. That's going to change RBP. Oh no, but the one issue, let's see here, One issue here is when you're setting up this open call, this is where the real issue is, I think. I'm surprised there's not a leave ret. Wait, but that's the equivalent. No, it's not. Oh, yeah, because we do an add. Either way, an issue is that we're referencing things relative to RBP as we start executing through this function. And if you think about the first thing you overwrote before you actually overwrite something important, being that ret adder, the return address, the very first gadget of your stack, you're actually overwriting the saved RBP as well. And the saved RBP is now going to influence what RBP is. And if you're not careful in how you overwrite that saved RBP, you can mess up these axes here that are going relative to RBP and cause a seg fault here, for instance, if you just completely randomly write a value to RBP. So this is something to be careful of when you start like trying to jump partway through a function, is that these functions do all sorts of like, they have very specific constraints on them. And so if you can, the best thing to do, or the easiest thing to do, is to just jump straight to the beginning of the function. Because if you jump straight to the beginning of the function, you'll see that whatever RBP was that we messed up, that value that like we maybe just destroyed, gets pushed to the stack, and then RSP gets pushed into RBP. So now, even though we destroyed RBP, if we jump to the beginning of a function, it doesn't matter that we destroyed RBP, because RSP is going to get moved into RBP, and now we have like a valid RBP to base everything off of. Hopefully that makes some amount of sense in terms of a pitfall you might run into if you're not careful and you try to just jump partway into a function, and you try to do that for multiple functions. In general, yeah, there's all sorts of issues that you might run into. Okay. Yeah, there's a question. Okay. Yeah, so the question is on level 7, it tells us the address of system, which means in some sense, once you know one address in libc, you know all addresses in libc. And the reason you know that, so let's just quickly look at this as an example, is here's what you can do to get the base of libc. It's just a relatively easy math calculation using pwn tools. So if we import pwn, and then we do, let's say elf equals this, and we'll go to level 7. And then I think we can actually do elf.libc, which will give us the basically the same sort of thing that this elf file, but in this case for the libc of that elf. If we take this elf.libc and we do symbols, so I can't scroll, can I? I don't know why that keeps happening. Okay, anyways, though we can still see it on the screen. We can see that the address of system is here. So if we look in libc for system, and let's just print that as hex, we can see that this is the offset from the base of libc. So all you need to do in order to calculate basically where everything in libc is, you can take this address, you can do minus this, oops, and let's make that hex. So this tells us now where the base of libc is, and you could now, if you wanted to know where, let's say, elf.libc.symbols send file is, you know where the address of send file is. So it's as simple as taking the reported system address, which was in that instance this value right here, and you should just subtract out where it is from the base of libc. So now you have the base of libc, and then you can add in any symbol and get there. So this, in that running execution, the address of send file is right here. So that's kind of how you can do that. Yeah, the elf object is extremely useful. Yeah, rather than, it basically saves you the hassle of having to do obj dump and like figure out where the address of something is. You just do this and it's basically going to report to you the same thing. There's also, on that note of kind of useful things here that might be useful, so there's actually elf.got and elf.plt in addition to symbols, because similar to how I was talking about with, you might want to do like a puts, where the outer puts is puts at plt and the inner puts is puts at got. You can actually get those values in this way. So you can do like elf.got puts, and we can do hex, and then elf.plt puts, it'll go there. And the reason I say that is because if we do symbols, I believe it'll give us plt. Yeah. So if we do elf.symbols, it's going to give us like the actual callable address. And the actual callable address is this PLT variant of puts, but you might be more interested in the GOT variant if you wanted to do that puts thing I was talking about earlier. How would you search libc for something like pop rax ret? Okay, so something, if you wanted to do that with elf, you actually, I mean, you could do it with elf. Let's quickly just look at that. So elf.libc or actually, hold on. So what we want to do basically is just assemble it. So if you're interested in this case, pop rax ret, you can assemble it. And then you could do elf.libc.search pwn.asm pop rax ret, and take the next of that, make it hex, and this is the address of a pop rax ret. Alternatively, you could use the Rop module to find gadgets, as we showed before. So if I did Rop equals pwn.rop on that elf object, and then I do rop.find gadget, and you basically give it a list of the instructions in that gadget. So it's not, rather than basically use a semicolon, you'll use like a comma. So you'll do pop rax, end of string, and then ret. And then, wait, is it not find gadget? Maybe that's not right. I think Rop is weird. Yeah, it's not find gadget. What was it? What is find gadget? Wait, did I spell it wrong? Oh, I did. Wait, did I? I'm very confused. Oh, in this case, I'm assigning it. Oh, interesting. Is there not a pop rax gadget? There's no way that's true. What? Hold on, let's see if pop RDI works. Okay, so it definitely finds pop RDI. Interesting. I don't know why there wouldn't be a pop rax. We'd have to be like no, there has to be though, because we found one. I don't understand. So definitely finds pop RDI. Should we like find anything in libc? Libc is massive. No, maybe not it. How did it not find syscall? Uh-huh. Yeah. That you can definitely do it with RP++. Interesting. I didn't, but with pwn tools specifically, huh. So you can definitely do this elf.libc.search method. Rop.findGadget. What does it say about this? Wait, what just happened? Oh, I'm still confused. Rop.findGadget instructions. Let's be crazy. Oh, this just goes through, I think self.gadgets is not actually all of the gadgets possible. It just finds a particular set, but why would it not find us an pop REX variant? Self.gadgets. Who creates self.gadgets? This person does. In gadgets.items, who created gadgets? Gadgets for elf and self.elves. Rop gadget. It's looking for these types of instructions. Yeah, you can definitely use RP++, but I'm definitely surprised that you can't do a find gadget for pop RAX using pwn tools. Why would it not? Huh. Wait a second. What's the key for gadget? Elf gadgets address. Well, that's fine. Gadgets update. That's going from address. Self. Huh. I don't really know, but either way, I think we found a. I think this other way would work, where we did search, where we just search the elf straight for the assembled bytes, I guess. So where did it think that pop RDI was? RDI. So it thinks RDI is here. If I do this to find RDI, does it agree? It might eventually agree. Let's do list to get all of them. And let's actually not print that because it might be a ton. Okay, so 479. If we do, wait, why is this? Instead of length, if we look to see if this address appears in here. Huh. Wait, what? Oh. Why is it not in there? Hold on, we're gonna only land or stay on this detour for a couple or one more minute. Let's see here. Hex E for E in this. Oh, this is gonna look terrible. 402. Wait. How many digits is this? 402 493. 42493. 2. Okay. Wait, is this all of them? How is it not finding it? Hold on, can we index into... So this is what we were wondering. Does elf.libc... Actually, what was Rop equal to? Are we like doing something dumb? I feel like this is what went wrong. Rop equals elf.libc. Okay, this is probably going to fix it. I think I see the issue. There wasn't a pop RAX in our binary, but there's definitely going to be a pop RAX in libc. But even still, you might not find exactly the gadgets you're looking for. Yeah, but it can find pop RAX. Yeah, that makes way more sense. Okay, so this resolves that issue. But yeah, you're probably not going to be able to find arbitrary gadgets because as we were looking through, I'm not going to look at it again, as we were looking through the source of pwn tools, which is kind of the best way to actually understand what these insane tools do, is it's not actually looking for all types of gadgets. But if you want an arbitrary one, I would be surprised. Actually, we can see now if this works. Wait, what? Hold on. So this gives us that. Okay, so elf libc search has, and actually let's go back to Rx just for the sake of it. Okay, and 4A5. Okay, hold on, we're almost there. Oh wait, these match up, yeah. Okay. Anyways, yeah, you can do, this should work for finding whatever particular gadget you're interested in. But in general, doing an exploratory process is probably easier with RP++ and grep. Yeah, probably, because this kind of implies that you know exactly what the bytes are of the gadget you're interested in, whereas if you do RP++ to just like print out every gadget that it can find and then grep for patterns of like sorts of things that might be useful for you, I would definitely say that in tricky situations where you need like, so obviously if you have libc gadgets, you're probably going to find whatever you want, just straightforward. But if you have like a small binary that only has a small collection of gadgets that like you don't have quite what you're looking for, or like what you're looking for isn't directly there, but maybe like a derivative of what you're looking for is there. So let me kind of explain this a little bit more because I think this is important for Rop. RP++, baby Rop, and then let's just do like R5 to get like all sorts of combination things. And let's find something that might better illustrate what I'm talking about. So like, let's say like move. Okay, so let's actually see if there's like a move, like something that lets us write to an address. So like in general, the pattern for like being able to move, actually we need, in general the wait, what? Oh, we need -p, don't we? In general, the pattern for being able to write to memory, which is potentially a primitive that you'll need, just in the general, if you want to write kind of like arbitrary programs inside of Rop, you might need to be able to write to memory. And what you'd really like would be like a, like we'll just write it out here. You'd really like a like move keyword like RAX comma RBX, for instance. Like this sort of thing would just allow you, if you have a pop RBX and a pop RAX, now you can just kind of write keywords to arbitrary memory locations. But we kind of grep for, so we're grepping for a move followed by some number of like alpha numeric underscore whatever characters. And then we're looking for this bracket because that means we're going to like dereference, which means we're going to like write somewhere in memory. So this is how you'd kind of start exploratory using RP++ to find tons of gadgets, and then use grep to kind of like think about the sort of pattern of a gadget you're interested in. If we were to just look for move keyword RAX, and we're probably need backslashes if we wanted to be completely honest with this, like RBX or something, right? Like I really want this gadget. Well, too bad, it doesn't exist. So you have to start using grep and kind of like coming up with patterns-ish of what your gadget might look like, something like this. And we can see some things pop out. It's like this doesn't look immediately useful unless you're like interested in writing here. But even if you're interested in writing here, like unless you're interested in writing a 1 here, this gadget probably isn't so useful. This gadget though is looking potentially useful. So this lets us write a single byte at a time, and we could like use multiple of these if we needed to write 8 bytes. And if we have like a pop RA, so now like we're thinking like, well, can we control RAX? And I think we already saw that there's not a pop RAX. Yeah, there's no pop RAX, but is there like a, we probably couldn't get away. What involves RAX? Maybe like we're not quite sure what we need with RAX, or maybe like a move RAX. So we saw this, and we're wondering like, okay, so let's say we want to control an address to write to. So it's like, is there something that's going to let us move into RAX? If we can't pop RAX, can we move into RAX? And if we start looking here, we can see that we can control RAX. If we can control this memory address, we can control RAX. You're kind of building up this tree in your mind of like, what are the constraints of all the gadgets I'm working with? Probably can't control that, so let's just ignore it. Probably can't control this. None of these are looking super great. Yeah, none of these gadgets really look like it's going to allow us to control RAX, and we need to be able to control RAX in order to control the destination of where we're going to write to. So for instance, what we're going to write, this DL, if we have like a pop RDX, which we don't, but maybe we have a like move DL or move R. We're not looking through libc. This is why this is so difficult, is we're just looking through a relatively small binary that's only going to have a few gadgets. No, this isn't even for the flag string. You could think this, I'm just kind of demonstrating the exploratory process of finding gadgets, which may or may not come up in later levels. But I think this is really useful to understand. So we're looking for, in my mind right now, we're kind of thinking about like, how can we write to memory? Which I guess, as you mentioned, we might want to write flag to memory. And if we could find a gadget that lets us write to arbitrary memory, and we know where a writable section of memory is, then we could use this to write flag to memory. Yeah, that's true. But we're not guaranteed to have the right primitives to do this. So we have to kind of like get creative with searching. So we kind of like got a little stuck on this RAX issue, but let's even see if we can control DL. And we can see that we can like move something into RDX, and if we can move into RDX, we're moving into RDL effective, or into DL effectively. But then we have to deal with this call, and this call might be a disaster, like might crash us, because then we have to be very careful about all of these things. Let's see here. These are all ending in like these call keywords, which is not great. do we have a move edx? Still with this call keyword. So like we could go on that if we could figure out how to control these things. So we can pop R15, which we can. And if we can pop RBX, which we can. Okay, so like maybe we are stuck with this insane gadget. We're stuck with this insane gadget that's going to require us to successfully dereference this address, but that might not be an issue, potentially, because it looks like we can control R15 and RBX, so like we could make this call succeed and do stuff. So now that means we can control DL. And that was all for looking at this, which means we can control this. We haven't quite figured out how to control this. That's probably not an issue. We would have to look up what this does. I have no idea what this does. But yeah, so basically I'm gonna stop here in terms of looking at this problem, but this is kind of, you might have to go down these rabbit holes. And this is why I say RP++ and grep is like really useful for the exploratory process of finding gadgets. Once you know your gadgets, sure, pwn.tools is fine. You can just make it find that specific thing that you already found. But for exploring for gadgets, pwn.tools is really not a good tool for that. Okay. Yeah, I'd be interested. Okay, so there's a question, and I think it's been repeated multiple times throughout this office hours. Or not by me, but asked multiple times throughout this office hours about stack pivoting. Yeah, so it would be helpful if you have a specific question about stack pivoting. In general, though, the thing to think about with stack pivoting, and I think that comes up in 7 and also later levels. The thing to realize, there's couple of angles on stack pivoting. So the first one is, let's just quickly objdump -d intel baby rop. Okay. So the first thing to realize about stack pivoting how do I put this? Basically, you're going to be doing a stack pivot as soon as you, just more insight on what it is we need to do. Okay, sure. So actually, let's figure out, is this the level that requires a stack pivot? Maybe it's not. Maybe that's 9. I think 9 does involve one. Anyways, yeah, okay. Yep, so we will quickly here talk about stack pivoting. Okay, so what it means basically at a very basic level or what it kind of means to do a stack pivot is you just need to modify RSP, right? So your entire, the entire way, maybe I can find something like this, sure. So as you execute your ROP chain, you're doing a series of pops, potentially interleaved with data, right? So you're kind of following along RSP. RSP is like this critical thing in all of this that kind of drives forward. You can think of it as, so normally a program's execution depends on RIP, the instruction pointer, and it still does in the case of ROP, but in some sense at a higher level, your instructions that you're executing, these ROP gadgets you're executing, are a function of RSP instead of RIP. I mean, they technically are also of RIP. RIP is getting modified, and that's what's ultimately executing it. But at a higher abstraction level, it's this RSP that's kind of driving your control flow and your execution. So if you think about it, before this executes, RSP is currently pointing here. And on our first way out of main, we're going to call ret. And ret is just a pop RIP. So you could going along with this analogy of RSP and RIP, you could kind of think of that ret as being the mechanism that shifts this higher abstraction of RSP being your execution engine to be RIP being doing the actual work, right? So when you do that ret that's going to execute this first gadget, you're doing a pop RIP. And a pop RIP, pop, inherently means what is RSP? So whatever is at RSP is going to become RIP. So that means this is at RSP, the address of this. So now we start executing this. RIP starts executing. And what's it going to use? Pop RDI. Pop RDI is going to take the next thing at RSP. So once we did that initial ret to begin our Rop payload, RSP is no longer pointing here. RSP is pointing here. So, but now RIP, so if you think of it as an abstraction level of, you have a one layer RIP is driving execution, but on a higher abstraction level, RSP is driving execution. When we do this to modify RIP, we're also modifying RSP. So now we're pointed here. And this is going to execute finally. We're going to do a pop RDI. And pop RDI is going to pull from what RSP is, pop it off the stack, put it into RDI. So now this 1 goes into RDI. And then this is sitting at RSP. But we're not executing this yet. You can kind of think of this as in the instruction pipeline. This is like next to go. But once we hit this ret, we do a pop RIP, and this does another shift from making RSP become our RIP execution engine, and we execute this. So what a stack pivot is changing RSP. So in all of this, we are changing RSP. Every time we do a pop or a ret, which ret is just a pop RIP, we just shift RSP by 8. But you could do something to shift RSP arbitrarily. You could have a gadget in here that moves, say we have some gadget like move RSP RAX. Well, now whatever the address of RAX is, whatever like that is pointing to, you could kind of think of it as like if we were to do like XX RAX, and maybe now this has like some abstraction of gadgets, right? Sitting at RAX is a bunch of gadgets. Well, now we're not going to do this linear, like we're no longer just moving RSP by 8 bytes with each pop. Now we're just like fundamentally moving RSP, which is fine. It just means that now if there was like a gadget here, so let's say we have a pop RSP gadget here. After this executes, whatever is here, so this is going to be some data. Let's say that this is like an address in the .bss. Well, now RSP is going to be pointing there. So what that means, and actually you'd have a pop RSP. Actually, this is going to be slight issue, isn't it? Not necessarily. You somehow were able to already control. Yeah. Okay, so what's going to happen here? I'm just kind of thinking through it in my head to make sure I'm not telling lies, even if it's mostly true. I want to be exactly true. So if we pop RSP here, let's just think this through. If we pop RSP here, RSP is currently looking at this. So this is going to become the address. This is going to become RSP now. This is where RSP, the value of RSP will be. So now when we do this ret to continue execution at the next thing, if you think of this as just like a linear set of bytes, it's not actually going to execute this. This will not run. because we just moved RSP, and when we do this ret, all we're doing is we're going to look at the current RSP and we're going to pop that into RIP. So now we're no longer continuing execution from this point. We're continuing execution from this point. Wherever the contents of BSS is, you could imagine, and BSS is a section in your program for things that are like basically initially null. It's global data basically. If somehow you'd already controlled BSS to contain data, so say we have like a win or whatever, if you can make RSP go here, it's going to continue execution from here. And if the win gadget is already here, well, you'll win. Hopefully that kind of, at least at a high level, if not also kind of like a deeper level, explains what a stack pivot is. You're changing RSP, which changes your chain. So the reason this is relevant, I believe in 9, is that I believe in 9, the mechanism of your data coming in is different. I think we still do a 4096 byte read, but we don't do that read onto the stack. We do that read into the BSS. And then I think we copy the first 24 bytes of that at like RBP. So basically you only have a couple gadgets. So you like need to quickly do a stack pivot. And where you want to probably pivot into is where all your data is. Yeah, exactly. Because you're actually reading 4096 bytes there into BSS, so you can have a ton of gadgets ready to go in the BSS. But you need to stack pivot to basically resume execution in the BSS. Because we read in your data into the BSS, but then we move the first 24 bytes onto the stack, so it's like kind of like your normal prior level ROP chaining. But you only have a small ROP chain. You only have these like 2 gadgets, I think, that you get to execute, or 2 addresses worth of data. So you could, but basically what you could do is you could fit this in there, right? To shift where execution will continue from, to do and this is what is the stack pivot. It's rather than continuing execution in this linear chain, you kind of branch off into some other part of the data and continue your ROP chain from there. Let me quickly get caught up on Twitch chat just to make sure, see if I need to go in more detail on anything there. One question is, how do we determine where to pivot to? So yeah, it's very situational, but if you have a memory with gadgets, like I guess that's a good place. And something else to think about, like it's extremely situational. So maybe you only get a couple gadgets and you don't actually get to write more data to the stack or somewhere else. Like you don't have control over other memory, but maybe there's a function pointer somewhere, like a win function pointer somewhere. If you could resume execution at that win function pointer, well, a function pointer and a gadget, like these are kind of like the same thing, right? You get to, if you can get away with just doing one gadget to win, right? AKA the win function. If you pivot your stack into that win function pointer, now the win function pointer will be your gadget that's going to be run next. And if it's the win function, right, you win. And I think that comes up on one of the levels. You put the gadgets there. So as I said, I think on 9, the way it works, so normally we do a read input buffer, or whoops, read yeah, let's look at 9 real quick. So if we run it. Let's just run it first. And this actually tells you kind of what that puts I was talking about before, because maybe you want to leak, maybe it's not relevant on this level. I don't actually remember. It says your input will be read to the BSS. So let's look at that. If we do obj dump dash d mintel baby rop less, let's go to main. Let's look for read. So we can see that RSI, which is the second parameter to this read call, right? Our DI will be the first one, so we're reading from standard in. RSI is where we want to read to. This is the number of bytes. We're reading to this RIP offset, which immediately should tell you that we are not stack-based, right? If we're RIP relative, that means it's somewhere like in the binary, right? It's in the BSS section. It's a global variable. If normally this looks like something that is like RBP relative, not RIP relative. So this is going to read into 1,000 bytes into the BSS, which means you have the ability now to put 1,000 bytes worth of gadgets in the BSS. But unfortunately, it's not like we do your stack pivot for you, right? You're still constrained by the stack, this ret instruction happening, being the thing that kicks off your ROP payload. And whatever is at RSP when this ret happens is what's going to execute. And we read your data not into RSP. Did my headphone just cut out? Can you say something? Oh, okay. I guess my left one will just start charging that. Hopefully it doesn't cut out. If I don't respond at some point, my headphones might have died. Anyways, we're wrapping up anyways. So as I said, this gets copied into the BSS. And we know that because this is RIP relative, not RBP relative. Then along the way, at some point, there's going to be a Mem Copy. Yeah, right here. So we're going to load we're going to do a Mem Copy from that input buffer that we read into on the BSS. And we're actually going to put it onto the stack. Let's see here. So this is where we want to copy from. So we're going to copy from the BSS. We're going to put it in whatever RDI is, which comes from RAX, and RAX comes from, this is add 8 to RAX, but this comes from here. So this is putting RBP minus 10, RAX, and then RBP. Okay, so we can see here, RBP gets put into RAX. RAX gets put into this local stack variable. Then that gets pulled back into RAX. This is just the compiler not being optimized. We don't run any optimization, so it's kind of like doing what the source code says directly. And then we add 8 to that. So whatever RBP is plus 8, which I think means we're going to be looking right at what this is going to be. And we copy 24 bytes. Hex 18 is 24 bytes. So I think that means we give you like 3 gadgets worth of stuff. And eventually your leave ret will run and it'll execute 24 bytes worth of stuff from what we read in, but you got to write in 1,000 bytes, so you do a stack pivot to get into that BSS. It's not quite so straightforward, so you might run into some issues in the BSS. You have to think about and the reason some people are running into issues in teaching, as far as I can tell, is that now that your stack is living on the BSS, you might be like more memory constrained. So when your stack is like where it's supposed to be, like we can see cat proc self maps. So when cat runs, the stack has, it's kind of hard to see, 20, from like 625B to 627C. It's got a lot of space to work with. Basically, it's the moral of the story. The stack is relatively, it's big enough. But the BSS, and maybe we can't easily see this by looking at cat, but the BSS is smaller. And you have to think that now that you've transitioned your stack, your RSP, into being in the BSS area instead of where it normally is, the stack area, function calls, if you start doing function calls and that needs to start shifting the stack to like put local variables in and stuff, if you go too far, you might start you could either start corrupting stuff, or you might not have enough space on the stack that you've created, which is in the BSS, to actually do things. There's all sorts of issues you could run into, because, I mean, your stack is no longer on the stack. The stack just suddenly became the BSS. So you can run into weird issues. People are running into issues with the teaching levels. Apparently, for a lot of people, 9 testing is actually easier than 9 teaching. Because 9 testing doesn't start doing these function calls. So if we look here, this right here, right, had to like come from a function call. And this is like calling into all sorts of capstone stuff that, like, it might get deep in the stack in terms of how much room of a stack it needs to use. And either corrupting stuff or going too far, like, stuff can start going wrong. But yeah, this is kind of like a nuanced issue you'll have to deal with. My headphones definitely just cut out. 1 second. Let me see. Can you... Whoa, wait, hold on. I think this is right. Can you say something? Oh, okay, yeah, I can hear you. Okay, we'll finish out the office hours anyways. If there's any final questions, I can answer them. Otherwise, feel free to ask in Discord. And remember that collaboration policy is the same as it was for the last module, where you basically just collaborate with people. Of course, the restriction is don't share flags. Don't give literally your script to someone. That's not okay. That would definitely be cheating. But in terms of like, hey, I have this issue with the BSS. How did you overcome it? Like, you can collaborate kind of like very detailed on these things. But yeah, don't give like your code away. Yeah. Okay. So is there any more questions? I have a small question in level 2. Can only get stage 1 to run. Is there anything I need to look out for that? Did you watch earlier in this office hours? So we covered level 3 pretty in depth and level 4 pretty in depth. And in doing so, I would be very surprised if I don't help you understand what you need to do for level 2. If you still have questions after watching that, feel free to message in Discord and I can try and help you with that. But hopefully these office hours that will be available to watch on Twitch and eventually YouTube, we cover level 3 and 4. So hopefully everything that we go through in that will help you with level 2. Yeah, we're still looking into the extra challenges imposed on teaching and trying to make it so teaching isn't harder than testing. Definitely give teaching a try, but a lot of people have reported that testing is easier than teaching. Yeah, so we added in extra levels than originally anticipated. So in some sense, you might think like, oh, there's 15 levels, that makes this harder. But the hope is the extra levels that we added in will make it so there's not like a huge difficulty jump. Because the issue before, we were about to launch less levels, but we noticed that there's like a difficulty spike that would have made going from, I think it would have been level 9 to level 10 just be like insane. And so we added in a new level 10 and also a level 11 to prep you for what was the old 10, which is now 12. And then we're going to add 13, 14, 15. As far as like pacing, I don't know. It's hard to say. Hopefully the difficulty is kind of like this gradual thing. And yeah, I don't know, just kind of solve as much as you can. Yeah, that's really all I can say about that. If you have any more concerns, feel free to like email me and Jan or whatever. But yeah, that's kind of where we're at. Yeah, so you can definitely watch this video here on Twitch, and we'll try to get it to YouTube as soon as we can. But Twitch allows you to watch the video as well, and that it will be available immediately. Approach to 5. I'm trying to remember what 5 was. Oh, yeah. Rather than write like flag to the stack, use data that already exists. So in the same way that you can find gadgets in the binary, you can find data in the binary, like the exiting string, for instance. All these strings. Yeah, and if you watch the video, that'll show you how to do that. All right, I am going to wrap up office hours then. If there's more questions, feel free to ideally message the help Discord channel. That way everyone can see it. If you have very specific questions, feel free to message me. But otherwise, yeah. All right, I am ending office hours now.